This video is going to be a somewhat, perhaps not too lengthy discussion about sampling distribution properties. Or perhaps better to understand it is, how do samples behave and what are their characteristics? Now, on the formula sheet is all the information you'll find all the information I'm going to present to you. It's on there. It's just written in a somewhat terse mathematical manner. The piece I want to point out is when you see capital N and then a bracket with mu and sigma in it, this is to be interpreted as shorthand for saying normal distribution. And it will be a normal distribution where the center is given by mu and the spread is given by sigma, typically your standard deviation, of course. Now, what is a sampling distribution? So remember that the word distribution can be nicely interpreted as properties, not properties, as patterns. So what are the patterns that repeated sampling of some population follows? That's what we're going to talk about. So the idea is that if you repeatedly sample a population, taking, a couple of dozen individual measurements and record the average value of those measurements. And if you repeatedly do that, at the end of the day, you're going to end up with a list of average values. And those average values, of course, come along with a standard deviation. In other words, they're numbers amenable to statistical analysis. That's the basic idea. And we're going to start by talking about how this works with means. So property number one on the formula sheet is written more or less as mu sub y bar is equal to mu. Now, how do you translate that into something meaningful? Well, remember I said over a course of time, if you repeatedly sample some population, you're going to get a collection of y bars. Well, this says the average of those y bars, in other words, I'm not going to try to torture you here, the average of the mean values is centered at the population mean. So let's write that out. I'm tempted to say the mean of the means, but you'd probably be justified in throwing something at me. So the average of sample means equals the population mean. And even that's too wordy for my preference. So why don't we say simply that the mean of the sample equals the mean of the population. So for example, if I said to you that y bar is 25 kilograms, what do you expect the population mean to be? Well, you would say, well, it's probably 25 kilograms. That's just what this tells you. English is treacherous. I was going to say that's what this means, but we've already been talking about means, and let's not torture the word too much. Well, if we have a measure for center, we should also have a measure for spread, and that's what point number two is. So point number two is the standard deviation of our sample means. Standard deviation of y bar can be calculated from the population standard deviation, that's sigma, divided by square root n. And we often see this, if this was s over square root n, we would call it standard error. But this is in the denominator of the z formula when we're working with y bar and mu. So this is just a simple computation. So let's write this out for what it is. This is the population standard deviation. And this is the sample size, under the square root, of course. So what happens then is the sample size gets larger and larger. The entire value here gets smaller and smaller. I'm going to summarize these points with a couple of pictures, and you'll see what I'm getting at with that. So the next two properties are simply sentences. First one's common sense. And it comes down to this. If the population is, and here's that notation, normally distributed, then any sample of any size will also be normally distributed. Boom, there it is. Makes perfect sense, right? It's number 4, the central limit theorem, that oftentimes is counterintuitive. But it does work, and the mathematics is proven. If you go looking up various central limit theorems on the internet, you'll have to sort through a handful. It's a commonly used term. But this does stand, and some accessible textbooks, when I say accessible, I mean easy to read at the undergrad level, provide good discussion and proof of the whole thing. Anyway, off to the library with you if you want to find out about that. Now, here we go. If the population is not normally distributed or has an unknown distribution, but, there's always a but, n is 30 or larger, so that's a magic number, by the way, then the sample will be approximately normally distributed. So this is where the magic number of 30 or more comes from. It comes from point 4 on this discussion of the properties of the sampling distribution as it relates to mean values. So all 4 of these can be discussed or can be summarized in 2 little pictures. So let's draw those. I'm going to make a new slide for the pictures instead of scrolling down on this one. This one's got enough on it. So let's take a look at this. Let's make a couple of bell curves first. So here's my first bell curve. I'm just going to freehand this. So here, so black ink is population. I need a little bit more headspace on that. So black ink is how the population behaves, okay? So the population has a mean value. And the population also has a spread, which is the standard deviation. Boom, like so. Now let's change colors. Let's use, we've got a blue here. My colors on this are a bit limited. Let's use that color. Now let's use red. That'll stand out better probably. If you're colorblind, I apologize for that. But the 2 things will be quite a bit different to see. So, how does the sample behave then? Well, the sample still has the same center, but it's narrower. So that means, so for the first thing property number 1 was the centers are the same. Property number 2 says that the spread is different. Look how much narrower this is. That's because we have sigma divided by square root n. And remember what I said earlier, as n gets bigger, the spread has to get narrower because you're dividing by a bigger and bigger number. So if you take this to its logical conclusion, we'll end up with a spike dead center. But of course, there's a couple of conundrums that go along with that. Generally speaking, there's a thing called the 10% rule. We don't worry about it too much in this course, but this is considered to be accurate until n is about 10% of the population size. And that's pretty hard to attain, actually, in most cases. Red is sample. In a country like Canada with nearly 40 million people, 10% is 4 million. That's a substantial sample. Well, it costs money to sample, so most of the time you're never going to get anywhere near 4 million people in your sample. It's only when you run into populations that are very, very small that this becomes a problem. So what's going on here? Well, what we have going on here is properties numbers 1, 2, and 3. Now let's make another picture and go 1, 2, and 4 to show this. We need another bell curve, so let's do that. But we're going to have one with a right tail. Guess that's not a bell curve then, is it? How silly. This is a force of habit when you're talking about these things. Okay, where's the center? Well, we're going to call this mu. This thing still has a spread. That's still standard deviation. Now let's go over here to red again. But now, due to property number 4, with the sample size being sufficiently large, we end up with this. So here, n is greater than or equal to 30. The centers are in the same place. I suppose I could, can I make that line up like so? There we go, I think so. And we have, again, our standard deviation, which is sigma over square root n. So here, even though we have black as a right tail distribution, and certainly not normally distributed, but because my sample size is sufficiently large, my sample is going to behave as if it comes from a normal distribution. So this is properties 1, 2, and 4. That's a nice way to summarize the properties of mean values in context of repeated sampling. I think I'm going to stop this video here, and then we'll have a further discussion about how these properties apply to proportions in the following video. So let's end this one now.